Hello and welcome back to this 11th lecture on bio microelectromechanical systems. We will just like to do a brief review of what we covered last time, where we talked in details about designing of the ion selective electrodes. We also tried to find out the Debye-Huckel equations and how it can be used for solvated ion transport. Basically we looked at the interaction of a primary ion of interest in an environment of the counter ion cloud, and try to derive something called the activity coefficient, which is also important for determining the participation really of an electrolyte of interest, of an ion of interest in an electrolyte over the several other competing ions. We tried to also define the Nikolsky-Eisenman equations, where the selectivity of a particular ion of interest over the other interfering ions and their contributions to the measured EMF were studied in details. For both the weakly and strongly interfering ions, we kind of compared how this EMF variation would take place, and we tried to solve several numerical examples to look at the different practical aspects of design of such electrodes. Today we will be starting a new topic on why these sensing protocols are really needed and how these can be used to detect some of the analytes of interest as we go by. We will finally converge into something which is very important in the area of biomems, which is surface driven flows in all these micro assays. Typically, as I have discussed off and on in my previous lectures, biomems devices do use a lot of microfluidics, and essentially microfluidics also is defined as the flow of fluids at the microscopic length scale. These flows can sometimes be totally driven by charged surfaces. These flows can be electrokinetic flows, electroosmotic flows, electrophoretic flows, so on and so forth. And so we will make a detailed analysis of such flows and then finally apply them to make novel mechanical devices like micropumps, microvalves, micromixers, etc. So this would form a small part of the curriculum on this bio microelectromechanical systems. So let us try to understand why these electrodes are used, or these ion selective electrodes are used off and on for sensing various analytes of interest. And most of these metabolites of interest are essentially found within the human body. And a very important goal is to try to design something which can take up various gases which are generated and try to identify some analyte of interest or a metabolite of interest in the human blood on the basis of these measured gases. So let us look at what we have covered so far in as regards the very important component of ion selective electrode, that is the membrane. So we have looked into glass membranes based pH electrodes. We have also looked into solid state based on crystal membranes like lanthanide fluoride. We have typically also looked into liquid ion exchange membranes like varenomycin. If you remember, this was a resin obtained from the extract of a tree. It was an organic resin, and also it is found in cell walls and they are used as molecules which furnish the transportation of calcium and potassium ions. And then we also talked about enzyme entrapped membranes, particularly if you remember about the glucose oxidase case. We described in details how an enzyme entrapped membrane can be able to pick up an analyte of interest. So just to let you know a few mathematical details about how pH electrodes are calibrated. So essentially, if you look at the Nernst equation for such an electrode, the EMF measured by the pH electrode would really be equal to the intercept, the Nernstian intercept, which is K, minus of the Nernstian slope 0.059. Mind you, in this case we are talking about hydrogen plus 1. So you have N equal to 1 here times P of H. P of H, as we know, is the negative log of hydrogen ion concentration, the negative log of the hydrogen ion activity or the hydrogen ion concentration in extremely high background electrolytes where there is a huge charge in the background. We can consider the activity to be same as the concentration as we remember from before. So E is equal to K minus 0.059 pH, and pH here can be identified as K minus E by 0.059. Okay. So, that is how you can find out the pH in the case of glass membrane pH electrodes. For the crystal membrane electrodes, like let us say lanthanum fluoride, which detects fluorine ions or fluoride ions F minus, the EMF in this case potentiometrically will be proportional to the logarithm of the activity of fluorine ions. Okay. And similar in a similar kind of situation, the activity can be equated to the concentration, or we can assume the gamma to be equal to 1 in that particular case. Okay. So, let us talk about gas sensors, gas sensing electrodes at the outset, to kind of know what is the basic schematic which is involved in such electrodes, and this would be kind of followed with a detailed analysis of why they are required, okay, as I pointed out again and again before. So, here in this electrode, if you look at, you have essentially a glass pH membrane, and this is a pH electrode. So, this right here in this region is the glass pH membrane. You also have a gas membrane here, especially for dissolving the gases which would be measured or which are intended to be measured in terms of a pH change. We have a reference solution here inside this particular concentric tube. Okay. So, this essentially is the concentric tube. So, you are separating this tube, filling it up with a reference solution or reference electrolyte, and this portion here is permeable to only hydrogen ions. Okay. So, this is the typically the if you may recall, the silicates of chalcogenides or group 6 metals, okay, which are able to select specifically hydrogen ions over the other interfering ions. So, here also we have another reference solution, okay, in this particular zone. So, you have a solution inside the glass membrane for the hydrogen ions, and you have a solution outside it, and we have two electrodes here, Re1 and Re2, which are both reference electrodes, and they would be able to sense any transfer of H plus ions into this particular solution here, okay, into the internal electrolyte here. So, essentially you are trying to detect the change in pH, okay, and how that is related to the analyte of interest is being reflected here below in the following area of the slide. So, essentially these are based on pH measurement, and they can detect gases from aqueous phases. The electrolyte contains, the electrode contains an internal electrolyte which will contain a material forming a buffer with the gas material between the glass membrane and the permeable or the selective membrane. So, essentially this is a concept of buffering. Okay. So, you are definitely trying to select something which would create a buffer material and would equilibrate with the particular gas that is being taken up from in this particular electrode. Let us suppose we are trying to detect the ammonia, okay, NH3, the system is trying to detect ammonia gas. So, electrolyte in that case would be ammonium chloride, okay, NH4Cl, and the way it equilibrates with the ammonia is given in these set of equations here. So, NH4Cl while you put it in a solvent, typically an aqueous based solvent, would immediately get converted into NH4 plus and Cl minus, okay. And then if we assume that there is an equilibrium relationship between the NH4 plus that is formed, or the NH4 plus concentration that is there within this electrolyte, and the ammonia NH3 and hydrogen ions and H plus in this following manner, NH4 plus is in equilibrium with NH3 and plus H plus. So, what would happen if there is an increase or decrease in the concentration of NH3? There would be a shift in the equilibrium either way, okay, and if this shift can be detected in terms of what is the pH of the medium, okay, what is the negative log of hydrogen ions in the medium, we are done with our measurements. So, we can find out what is the concentration of NH3 based on studying the equilibrium properties here in this particular reaction, how it shifts both ways with respect to the production of H plus, okay. So, essentially we can also write all this down in terms of an equation which would be able to directly read the concentration of NH3. How? So, let us look at, or let us frame that equation. So, you have a case here where the equilibrium constant Ka of this particular reaction can be written down in the manner Ka equals the concentration of the products, which is NH3 times H plus raised to their coefficient, stoichiometric coefficients, which are 1 in this case, divided by NH4 plus, the ionic phase in the liquid electrolyte or the ammonium chloride solution. Okay. So, essentially if we take logs on both sides, you have log of Ka here equals log of NH3, right, concentration, plus log of hydrogen plus minus log of NH4 plus. Okay. And so, therefore, log of NH3 here really would be defined as, this here is minus pKa, if you may recall. It is that is the way the pKa would be defined, all right. So, it is minus pKa. So, you have minus pKa plus log of NH4 plus, which is actually the concentration of NH4 plus, and you have plus pH. pH again is negative log of hydrogen ion concentration. This is transferred to the left side, has a negative coefficient, and this becomes minus pKa plus log of NH4 plus pH. So, you have a direct readout of NH3 concentration, the logarithm of NH3 concentration, if you can measure these different parameters, the equilibrium constant, the NH4 plus concentration, and the pH. Okay. So, Ka of course is also known as the acid dissociation constant. If you may just recall a little bit of fundamental chemistry, this is essentially a Lewis acid. It has capability of getting protonated. So, NH4 plus gets protonated, or it protonates, and it generates a hydrogen ion and it converts into NH3. So, the electrodes for the other gases, that is sulfur dioxide, nitrogen dioxide, okay, and these are essentially sometimes polluting gases of the atmosphere also. Carbon dioxide or hydrogen sulfide, so on and so forth, are measured by identical techniques using one or the other equilibrium process, just as you saw in the case of ammonia here, okay, and they are constructed pretty much in a similar manner. So, let us look at what these gas sensing electrodes could do. So, essentially one thing that they could be used as very appropriately is actually as a potentiometric biosensor. Okay. So, essentially if you recall, potentiometry is again a form of electrochemistry where the voltage or the EMF is proportional to the concentration of the particular solution, or the concentration of the analyte of interest at, of course, 0 current. Okay. So, you are essentially limiting the current to 0 and trying to measure how the EMF of a system would vary with the change in concentration of the analyte. So, potentiometric biosensors are very useful because a pH sensor is essentially a potentiometric biosensor, and so as in most of the cases you see there is always either an addition of a hydrogen plus ion or consumption of the hydrogen plus ion, and there is a shift in equilibrium because of that reason. Almost always, you know, the pH linked method can be used for measurement of certain analytes. So, let us look at some of the analytes which are important from the bio perspective. So, before doing that, so we can define them as the simplest potentiometric electrodes applicable to any system in which there is a change in pH during a chemical reaction. Okay. So, an appropriate enzyme has to be mobilized sometimes onto the sensor, which is also known as the recognition element, if you look at the sensor model which we did earlier, which will decompose the analyte of interest to produce a hydrogen ion, and an increase in the hydrogen ion would mean a reduction in pH, and therefore you can accordingly measure what is the concentration of the analyte which is broken down. So, the first application is in terms of penicillin detection. If you recall, penicillin is an antibiotic, okay, and it's administered in most of the times in patients, and sometimes so for a variety of different infections, and there is a huge problem of related to infection. Sometimes there are allergic behavior of the particular patient to penicillin. Okay. So, therefore, there is supposed to be some kind of a bedside care which you have to provide to kind of detect. Suppose there is an allergic response like this to a patient. The first guess, which especially post surgical patients, okay, the first guess which the doctor would have is it might be due to an antibiotic like penicillin, and so therefore it is pertinent to kind of decipher the penicillin concentration of the patient's blood sample, okay, and then relate that to the allergic behavior or the allergic response that the patient suffers from. So, the way you do it is very simple. You design again a pH based electrode and use an enzyme here, the beta lactamase. So, penicillin, as you see here in the first equation here, or first chemical reaction here, in the presence of this catalyst, the beta lactamase converts into penicilloate, which is again it's a kind of reduced form of penicillin, and it actually liberates a hydrogen ion here, okay. So, the penicillate that is produced is essentially one charge less or one valency less than the penicillin, okay. And so, it produces a hydrogen ion getting reduced by the beta lactamase, and then this hydrogen ion can be easily measured by means of a pH electrode, which would give you a basis of the concentration of the penicillin in the patient's blood sample, okay. Very often we also would like to measure several other analytes or metabolites in the patient's blood sample, one of them being glucose. Particularly people suffering with hypo and hyperglycemia would need a thorough investigation, probably on real time basis sometimes, of the blood glucose level, okay. And it is more so needed because sometimes there is a requirement of additional insulin, and the system, if it can decipher either a raise or a fall in the blood sugar level, would accordingly release a certain dosage or stop the dosage from being released of the insulin, particularly in patients who suffer from these hyper and hypoglycemia syndrome, okay. So, the way you detect glucose is very simple. Again, you try to oxidize the glucose by another enzyme called glucose oxidase. If you see equation number 2 here, it talks about how glucose has been broken down. So, glucose essentially in the presence of oxygen and in the presence of this catalyst glucose oxidase, it is an enzyme, would convert into gluconic acid and H2O2, okay. Now, gluconic acid being an acid would essentially change the pH of the medium. So, this is an acid, and so it would result in a decrease in the pH of the medium because of an increase in the hydrogen ion concentration, and therefore we can safely assume that if the glucose concentration can be deciphered by looking at the pH based on the formulation of gluconic acid, okay. Similarly, another very important metabolite of interest is blood urea. Blood urea is essentially indicative of renal problems in the patient, particularly patient with kidney problems, renal problems in the renal system. They have this tendency of the blood urea level to be uncontrollably high sometimes, and so therefore it is important to try to find out what is the abnormality by looking at the urea concentration in the blood sample of the patient. And so therefore one good way of looking at urea could be by again using a pH based electrode. If you look at this particular equation here, it talks all about urea, which is CONH2 whole twice, which actually kind of hydrolyzes in the presence of water, and this enzyme here urease which converts into NH4 plus. This is the acid which is generated, the Lewis acid which is generated, and CO3 minus 2, okay. So therefore an increase in NH4 plus concentration would indicate again an increase in a reduction in the pH, because it is essentially acidic. It is a Lewis acid, okay. It has an additional hydrogen ion here. It can actually go very well with the kind of electrode that we have been discovering or discussing earlier in the earlier slide by using the ammonium chloride solution of the electrolyte. So therefore with the aid of a suitable buffer solution, one can measure this reaction like buffer solution like NH4Cl, as we saw in the last slide, okay, over a pH electrode. The pH measurement here would be indicative of what is the urea concentration in the patient's blood. So these are some of the illustrations of how potentiometric measurements can be made effectively for biosensing, particularly of metabolites of biological importance, okay, related to the human body. So there are some other examples here that I would like to discuss. There can be ammonia linked biosensors, where you effectively also are able to find out how the ammonia varies. Again, it is through a pH measurement, as we saw last time, using NH4 plus and Cl minus, that is ammonium chloride electrolyte, and equilibrating the ammonia gas with respect to that, and being able to tell the concentration of ammonia based on the concentration or the change in concentration of the hydrogen ion. Okay. So, here again similar kind of setup is used, that instead of for chloride you use the corresponding hydroxide. So, if the ammonium hydroxide is added to the solution which is being probed with the urease immobilized, and urease, if you recall, is the enzyme which is able to catalyze urea into NH4 plus and CO3 2 minus, as we just did in the last slide earlier. So, this urease immobilized ammonia selective electrode or a standard pH electrode would be able to very well define the amount of ammonia in equilibrium with the ammonium hydroxide solution. So, instead of chloride we are using a hydroxide here. Let us look at the reaction here. CONH2 whole twice hydrolyzes in the presence of water and the presence of urease enzyme to formulate 2 NH4 plus and CO3 2 minus, and the NH4 plus further actually equilibrates with the ammonium hydroxide solution here NH4OH to formulate 2 NH3, and this is ammonia plus H2O plus 2H plus. So, in this stage or in the later stage where the ammonia can be kind of equilibrated with the NH4Cl or some other electrolyte, we could measure the pH and be able to tell what is the ammonia concentration, and correspondingly what were the urea concentration as borrowed here from the last step. Okay. So, that is how you can measure urea independently also by just using an ammonium measurement method, although effectively everything is based on pH measurement. There are some other analytes of interest within the human body. One which again tells a very good information or gives very good information about the renal system is creatinine. Okay. So, creatinine is essentially stored as a phosphate form and is phosphorylated form of the creatine molecule. It is an important energy store skeletal muscles. Okay. Essentially it converts anaerobically the ATP, the adenosine triphosphate, into diphosphate form, and this results in the formulation of a creatinine moiety. So, therefore, especially in the muscle cells when you work out, okay, and the muscle is starved of oxygen, sometimes the human body is such, the blood essentially in the human body is a great transporter of oxygen. So, as you run the heartbeat increases, right, and why is that so? Because oxygen has to be delivered at a huge amount or a huge rate into the various tissues within the human body as you work it out. Sometimes the heart of a patient not being normal, a normal patient may malfunction, due to which there may be a requirement of oxygen. So, in that case how the body manages again is a very effective way, in a very effective way. So, what it does is it again converts the stored ATP, the adenosine triphosphate, into the ADP or the diphosphate form, and this is at the cost of creatine. Okay. And essentially this is done anaerobically, that means in the absence of oxygen. So, even though the oxygen reaching the particular muscle tissue is lesser in amount, still it is able to harness its energy or generates its energy. But creatine produced within the body creates a problem because it has to be filtered, and the kidneys are effectively the filtration mechanism for all the body, as we all know, and the blood essentially it is a purifier for metabolites like blood which flow through, and harmful products are secreted out of the human body. Urea is one of them, blood urea is one of them, and another is creatine. So, creatine, if generated or if it goes unfiltered, is also indicative of that the kidneys are malfunctioning. So, we can very well find out the renal health by looking at the creatine levels within the human blood. So, creatinine again, if you look at, is essentially with a mechanism or with an enzyme called creatinase, would decompose into NH3, the ammonia, and creatine. Okay. So, essentially because there is an NH3 component in this particular reaction, we would be able to ascertain how much this equilibrium would shift to what side as the NH3 is produced less or more. The NH3 can be produced or measured of course by using a ammonia based electrode, as we have talked about before. So, the creatine level, if it goes high, it automatically means that it is at the cost of more creatinine, and that means more ammonia is generated. Okay. So, that is a way of finding out how the renal health is functioning of a particular body. Another interesting example is to measure the phenylalanine. It's an alpha amino acid which can be converted into triosine, which in turn makes this molecule DOPA. Okay. So, DOPA essentially is again it's a molecule which is responsible for generating these hormones called catecholamines. There are about close to 12 endocrine glands within the human body, okay, and I'm sorry, about 8 or 9 endocrine glands within the whole human body, and these glands are essentially the cause of secretion of these uniquely functioning organic molecules called hormones. So, essentially what the hormones do is they upregulate or downregulate certain physiological processes within the body, and there are these adrenaline there is these adrenal glands within the human body which are able to generate these catecholamines, particularly in stressful situations. Okay. So, in situations of extreme physiological stress, or maybe just low blood sugar giving the stress or causing the stress, there is a huge generation of these catecholamines. Okay. And so, this catecholamine is essentially a function of the DOPA molecule, or the presence or absence of a DOPA molecule. So, these are all very interrelated. So, it all starts with this cycle from this basic alpha amino acid phenylalanine, and so therefore, it is important to measure in the phenylalanine content in a human body for understanding whether the endocrine gland is able to generate, or the adrenal gland is able to generate sufficient amount of catecholamines, which keeps the body kind of going, okay, in terms of in stressful, physiologically stressful situations. So, how do you do that? There are ways and means of finding out. Some of the catecholamines, by the by, are like epinephrine, norepinephrine, dopamine. All these different moieties are essentially produced from the molecule DOPA within the body. They are, but the root cause of all that is the amount of the alpha amino acid phenylalanine. So, phenylalanine is actually composed again by this molecule called phenylalanine ammonia lyase, as can be seen here, to convert or to get converted into NH3 and this trans cinnamate. Okay. So, this is again another organic species from phenylalanine. So, again measurement of ammonia would be able to ascertain how much amount of phenylalanine is there in the metabolite of interest, or the blood of the patient of interest. Another kind of measurement that we often do is this adenosine measurement. You have another enzyme here called adenine deaminase, which converts into NH3 and inosine, and essentially these are all measured by ammonia electrodes. So, I am just trying to give through a few of these slides some flair of what actually goes into the biodiagnostics or the clinical diagnostics area as regards human patients. All these sensors are very important from the point of view of measuring the different physiological conditions of the human body. So, following this, we can look into some carbon dioxide linked sensing mechanisms. So, we have already covered pH, as you did in the first slide, followed by ammonia based, where these different analytes of interest were recorded using ammonia, and then trying to essentially look at it through the pH electrode, but then equilibrating that with some kind of a salt solution of ammonia. And now we will be looking into carbon dioxide. The process is pretty much similar as before. You can make it using a reading for NH4 plus, or you can make it using some kind of a equilibrium between carbonic acid and the CO2 or CO3 minus 2, which is generated as a result of different chemical steps. Okay. So, we can again detect urea, blood urea, by using carbon dioxide sensors. So, if we make solution acidic in reaction described below, it will generate CO2, and this may be detected by a CO2 electrode. Okay. So, let us say urea CO NH2 whole twice hydrolyzes in the presence of ureas, as we know, to convert into 2NH4 plus and CO3 minus 2. So, if I take this component of this reaction instead of the NH4 plus, okay. So, if I take CO3 minus 2 component of this reaction, and then convert it by mixing it with some kind of a acidic solution, okay, where you have an excess hydrogen ion, you get converted into H2O and CO2. So, it produces carbon dioxide, but at the cost of reduction in the hydrogen ion concentration. So, there is a change in pH, and you could detect how much amount of CO2 is produced by looking at how much amount of reduction in the hydrogen plus ion concentration would typically take place. So, that is how you can using a carbon dioxide based sensor be able to tell urea. So, on one hand, in the earlier slide you saw that we measured using the NH4 plus and an ammonia biosensor, and in this case we are using the CO3 minus 2 and a carbon dioxide based electrode to measure the same level of urea in the blood sample. So, at different times, you know, you really need to use different sensors, okay, based on the availability or inavailability of many you know, species or conditions within the human body. Particularly in case of implantable sensors, this is a very common problem, that not all places of the body would have all analytes of interest, okay. So, there are some places which are starved of a certain analyte, and there is some other space where there may be abundance of another kind of electrolyte. So, you design your electrodes or design your sensing mechanisms based on what is available at what portion of the body. Another important aspect is oxalate measurements. We all are aware of this critical problem related to kidney stones, okay. So, that is essentially also medically known as hyperoxaluria. So, essentially more amount of oxalates in the patient's blood, again suggesting a renal abnormality would mean the accumulation of such oxalates, and through that there may be problems related to stones or, you know, these calcium deposits in certain areas of the kidney or maybe parts of the gallbladder, and it is of importance to detect the oxalate level in the human blood just to monitor whether a patient is inflicted with this problem of stones, okay. So, calcium oxalates formulate kidney stones, as we are all aware of this, and this essentially means abnormally high level of oxalates in the urine, and how we can detect that is again through a carbon dioxide based sensor. So, there is this enzyme called Oxalate Decarboxylase, which can break down oxalate into CO2 and form it, okay. And you can measure the CO2 using an electrode like the above as you saw here, okay. And essentially that so if you put this in equilibrium with this particular reaction, you might be able to formulate an idea of how much oxalate was there in the patient's blood. Alternatively, you could also convert oxalate using another enzyme called oxalate oxidase, okay. In this case the enzyme was different, it is decarboxylase, this is oxidase, and you get converted into CO2 and H2O2. Again you could measure it using a CO2 sensor by finding out whether the CO2 level has gone up. So, in principle we have more or less covered the different kind of gas sensors that are used for different bio applications. I would like to now go ahead with another very interesting and important phenomena of what we call the double layer phenomena, okay. As I told you before that in microscale flows a very important problem is surface charges. The charges on a particular channel surface, microchannel surface, would actually relate to developing a density gradient of the opposite counter charge of the solution, and this could be a basis of movement of fluids within small capillaries. So, let us look at this problem a little more closely and try to make an analytical model for this particular problem. So, let us say the interface between, so let us first try to find out what happens to the interface between a pair of conducting phases. The phase can be a solid electrode, could be two liquids, it could be you know, a liquid and a solid, or it could be a solid and a solid. So, at the interface between any pair of conducting phases, there always develops a potential difference, okay, due to the formation of this double layer. We have been off and on talking about what the double layer is in our earlier electrochemistry lessons, okay. So, the various types of interfaces can be following. It can be metal electrolyte interface, it could be a metal and a metal, it could be an electrolyte solution with another electrolyte solution, or it could also be a solution of a lower concentration separated by a semi permeable membrane with respect to the solution of a higher concentration. If you may remember, in one of our electrochemistry lectures we have talked about this kind of an electrode where there are two different oxidant concentrations, and there is a boundary between these two, and this can be an alternate means of designing an ion selective electrode. Okay. So, the electric double layer really, if you look at it, arises from an excess of charge due to ions, electrons or dipoles. Okay. And this is more kind of diagrammatically or visually represented by this particular figure here. Okay. So, essentially this is representing an electrode and its behavior with respect to a solution which is adjacent to it. Let us suppose that this electrode surface has a tendency of getting a negative charge. If you remember, zinc leaves the metal surface into the solution and gets into zinc ion, okay, thus leaving the electrons on the surface of this particular electrode. So, therefore, there is a negative charge on this particular surface, and there is a positive ion, or there is a bunch of positive ions which have left this surface into the solution, which are formulating this particular layer. Okay. So, essentially when these ions separate out, they have this small layer of water. As you know that this interface between a solid and a liquid, right, it is an interface between the solid electrode and a liquid. So, the liquid always is aqueous in nature, almost always aqueous in nature, and so there is a tendency of this layer of water or water molecules to come in between as a dielectric between the positive charge and the negative charge here, and so it gets separated with this thin dielectric layer of water. Okay, so we were talking about this electrode double layer, and this as I have represented here is essentially the formulation, the formulation of the double layer essentially. Okay. So, here the interesting thing to be seen is that the number of electrons being small is always almost responsible for creating a certain charge density on the surface of this electrode, as opposed to the number of positive ions which are in the solution. Okay. So, the electrons here in the surface are densely located, and they would create dense amount of charge because of their smaller sizes. The electrons are always smaller in size than the corresponding metallic ion in the solution. So, one of the outcomes of this kind of a size difference between the negative and the positive charge centers would essentially result in a thin amount of charges because of their size restrictions, or its bigger size, and really the first layer here separated by this layer of water molecules will not be able to totally neutralize the negative charge on this electrode surface. Okay. So, let me just come again with this idea that you have these positive layers here, positive charges here, which are bigger in sizes than the negative charges correspondingly in due to the electrons on the surface of the electrode. Okay. And the first layer really, the first layer which is represented here, which is just about separated by this layer of water molecules dielectric, would not be able to neutralize the total amount of negative charges here because of the greater sizes. So, what would be an outcome? The outcome would be that these layers would kind of still be able to hold positive charges, and the density reduces with distance again, and the neutralization would occur somewhere in the bulk of the solution, somewhere in the bulk of the solution. So, therefore, there would be layers of charges, okay, in the solution with decreasing intensity or decreasing density of these charges till and until the whole negative charge on this electrode is neutralized because of the positive charges in the solution. So, this brings us a very interesting characteristics. It essentially tells us that whenever there is a surface in close proximity to a solution like this, there would always be a distribution of charge of the opposite kind as the surface more into the bulk of the solution. Okay. That is number one. And number two is that if we have this distribution of the opposite charges to that of the surface on the bulk, then we can as well use these to flow the whole fluid, particularly when the length scales that we are talking about is close to the length scales of this bulk charge layer. So, we essentially from the days when it was first this theory was proposed, identified the first layer of charges here, which is close to the electrode, as also the outer Helmholtz plane. Okay. So, the first layer of charges which is directly facing after this water layer is crossed over from the electrode is known as the outer Helmholtz plane. Okay. And so, this other layer which is going into the bulk of the solution is also known as the bulk charge of the particular solution. Okay. So, in summarily, for the case of an electrode dipping into a solution of an electrolyte, the total charge on the electrode surface must be balanced by the total solution charge, which is also the opposite charge, and therefore, there is a tendency of a distribution of charge within the bulk for obvious reasons. So, there is an electrostatic interaction between the electrode charge and the solution charge. Okay. Ions from the solution may approach the electrode surface only so far as their inner solvation shells, and the inner solvation cells is essentially this single monolayer of water which is separating both the ion of interest or the ion in the solution and the negative charge on the electrode, and the surface array of the ions is thus cushioned from the electrode surface by this monolayer of dielectric, which is water. Most of the electrolytes are actually immersed in aqueous based solvents. So, you have water as the carrying medium in most of the electrolytes. So, the line drawn through the center of such ions at this distance of closest approach marks a boundary. We call this the outer Helmholtz plane. Okay. And the other portion of the charge, the cancelling charge away from the electrode as the bulk charge on the solution, and the size of the ions forming the outer Helmholtz plane are larger, and the total number of ions need to do a complete charge balance, and because they cannot be fitted on this one plane, they have to go into the bulk. Okay. So, this is also known as the bulk charge or the diffuse layer or the diffuse charge in the solution. So, the remaining charges are all held with increasing disorder in the outward direction into the bulk of the solution. So, they are also known as the bulk charge of the solution or the diffused part of the double layer. Okay. So, it is called the diffuse layer or the diffuse charge with respect to an electrode. So, in a sense, this is the dynamics of the double layer, which is formulated when electrode or one phase, be it solid or liquid, comes in contact with another phase. So, let us do some detailed modeling and studying of how we can use the Poisson's equation to find out the behavior of potential as we move in an outwardly direction from the electrode to all the way to the solution. Okay. So, a couple of interesting things are that if we plot the potential with respect to the distance, the variation of the potential, let us say psi in this case with distance from the electrode surface is linear as long as it is between the inner solvation shell or layer, and then it falls down rapidly into the bulk as it crosses the outer Helmholtz plane. Okay. So, all the charges which neutralizes that on the electrodes is held in a region called outer Helmholtz plane. So, up to the outer Helmholtz plane, the electric field drop is linear, as if it shows that in this region really it is a resistive drop, because the only thing which is available here is a layer of dielectric. Okay. So, it is a layer of huge resistance. So, you have a case here in this particular region where there is a drop in potential, it is a resistive drop, and then in this particular portion, as we will be shortly calculating how this varies or what the potential here is, okay, in this particular outer Helmholtz plane, this is also of great significance, especially to microfluidics. So, we will be calculating what the potential here is and what may be the distribution of potential as we go from this particular outer Helmholtz plane all the way up to about the point where the diffuse layer ends, okay, or the bulk charge layer ends the solution. So, this situation is similar to that of Debye-Huckel theory as we had generated for a single point ion. Of course, in this case it is not a 3D case, it is more a 1D or one dimensional, and this needs to be considered in the direction normal to that of the electrode surface. So, here for calculating the potential we can consider just one direction normal to that of the electrode surface and try to understand what is the variation of the potential phi with respect to that direction x. Okay. So, let us look at into a little bit of modeling. So, essentially here as we see in the one dimensional case really there are a couple of interesting things. One is the Poisson's equation can get converted now mostly into the partial of psi with respect to x twice equals k square times of psi. If you remember this essentially was also minus 4 pi rho by d. Okay. This was equal to k square psi. This is something I am borrowing from the earlier Debye-Huckel equation that we just about solved in the last few lectures. Give me a minute. This is the square of k. Okay. So, some interesting facts about this outer Helmholtz plane, that if you remember when we talked about the counter ion cloud, and the radius equivalent of this cloud, we generated a term which was equal to 1 by k plus A. A was essentially the ion size parameter, okay, the ion size parameter, and k was something that we assumed to be the equivalent of whatever the charge term was in the Poisson's equation here. So, this is essentially the effective ion radius. So, in case of the electrode, the 1 by k is replaced by the thickness of the diffuse layer delta. Okay. So, here if you see really delta is away from this outer Helmholtz plane all the way when the potential drops down to 0. The diffuse layer of charge or the bulk layer of charge ends really up to this point here when the potential phi is 0, and so delta is essentially the distance between the outer Helmholtz plane and this particular layer where the potential ends up to be 0 or where the diffuse layer ends, okay, in the bulk of the solution. So, the 1 by k here is replaced by delta. This actually comes out from another theory which is beyond the scope of this course. It is the theory of ion association as predicted by the Debye-Huckel theory. So, I will just assume here that this 1 by k is equal to delta in case of an electrode, just to make life simpler, and we will not be really looking at why that is so. Okay. So, just you can just remember this, and you can actually later on maybe do a reference search where you can see the theory of ion association. As explained by the Debye-Huckel equations. Okay. So, then let us try to solve this Poisson's equation here, equation number 1, and see what the solution would look like, or what the form of the solution would be like really. So, essentially d2 xi by dx2 is equal to square of k times of xi. The general solution for this kind of an equation can be represented as xi of x, mind you xi is the potential drop is only in one direction, that is perpendicular to that of the electrode, is a e to the power of minus kx plus b e to the power of minus kx. Okay. So, that is what the solution for this, I am sorry, this is plus kx, this thing is plus kx. So, this is what a general solution of this equation 1, the differential equation here, would be looking like. If we apply the boundary conditions at x equal to 0 or x equal to infinity, this I infinity is actually 0. So, applying this boundary condition, This can only happen if B is 0. Okay. So, if x is infinity, this term here goes all the way up to down to 0, but this goes to infinity, and therefore, the only way that phi infinity, xi infinity here, the potential at infinity here is 0, could be if B is 0, okay, because then it would take care of this infinitely growing term. This automatically is 0 by virtue of e to the power minus k x converging to 0. So, therefore, phi x is really a e to the power of minus k x. Okay. So, we already know that the real Poisson's equation is really in terms of the charge density. So, minus 4 pi rho by d, d was the dielectric constant, rho is the volume charge density, and that was equal to this k square xi as we have talked about earlier, right. So, if we put the xi value here in this particular equation, we get minus 4 pi rho by d equals a e to the power of minus k x times of square of k. Okay. Therefore, the charge density also can be represented as minus a k square d divided by 4 pi, okay, e to the power of minus k x. So, that is what the volume charge density rho would be in this particular case. So, let the charge density on surface of the electrode be sigma. Okay. We are making a presumption here that because we are talking about an electrode surface, as you look at here in this area, the dynamics of the charge density on the bulk layer or the outer Helmholtz plane is really driven by the amount of charge density on the surface of the electrode. So, it is a very critical parameter, and somehow we need to put this into our model, so that based on this charge density we could predict the nature of the diffuse layer or the outer Helmholtz layer. The only factor that I would like to mention here is that the basis of this density of charge would be the dependency on the surface of a particular electrode. In case of microchannel flows, electrokinetic microchannel flows, if the surface is silicon, there would be a certain bond density, and there would be this huge number of silanol bonds on the top of the surface, which would give it a negative charge, SiO minus kind of moieties, as it exposes to a certain pH or a certain solution of a certain pH. So, if this kind of a treatment is given on the surface, there is a tendency of the fluid to develop a diffuse layer which is of positive charge, or there would be a counter ion cloud which is of positive charges, and therefore, the surface charge density would be a function of how many active sites are there on the surface really, which can get silanized, which can get converted into SiO minus. Okay. So, we would look at this part of the solution in the next lecture. Thank you.